Up till now in physics, when we talk about motion, we talk about it in sort of like a Newton's first law sense, right? An object at rest stays at rest, and an object in motion stays in motion unless acted on by a net force. So we have this sense that something that's at rest will stay at rest unless there's a net force. And that's why when we looked at translational equilibrium, we often had these situations where we were looking at static equilibrium, an object that's at rest. And if we knew it was going to stay at rest, then we knew there had to be a net force of 0. But I want to get a little bit more sophisticated in how we talk about motion and being at rest. So Newton's first law sort of applies to translational motion. And I think of translation as a type of motion where an object goes from one location or one position to a different position. After the motion, it's in a different location, a different position than it used to be. But there are other ways an object can move too. So in addition to translation, there's rotation, where an object can more or less stay in the same location, but just kind of twists in a circle or some other shape without actually moving. It rotates. And it turns out that objects can rotate even if the net force is 0. So from here on in, saying the net force is 0 means that an object at rest won't start to translate, but it doesn't mean it won't ever move. It could start to rotate. There's another type of motion in addition to translation and rotation called vibration, where an object more or less stays in the same location, but just, as the word would suggest, vibrates or shakes back and forth, very, very small amounts, but very, very quickly. That's a type of motion too. So translation, rotation, vibration, these are all different ways an object can move. And if we're interested in translation and whether an object might start to do that, we have to look at forces. But if we're interested in rotation and whether an object might start to do that, we have to look at what are called torques. So a body in translational equilibrium will have no acceleration in the x or y directions. However, it could still begin to rotate. Consider a teeter-totter with a 100 kilogram student on one end and a 50 kilogram student on the other. Okay. And I'm interested, what would the net force be on this teeter-totter in the x direction and in the y direction? Well, let's do a real quick free body diagram. So we've got a force from this guy going down. That's going to be an Fg. That'll be pretty big. 100 kilograms is a decent mass. And we've got a force of gravity on this other side going down. That'll be half the size because this student is half as much mass. So this is a different Fg. We can call these Fg1 and Fg2 if you want. Now those are not the only forces acting on this teeter-totter. The fulcrum or the support here is going to be holding the teeter-totter up, stopping it from accelerating downwards. So we can draw that force. It'll be going up like this. And we'll call that the normal force. And okay. Now, what you know about teeter-totters probably tells you that no matter how you set up a teeter-totter, it's not going to start levitating off the ground and accelerating up into the air, right? It might twist a bit, but this fulcrum is going to kind of stay on the ground. Teeter-totters don't fly. So that means it's in the y direction, it's at rest, and it's going to stay at rest. So I would say in the y direction, we have the net force. In the y direction is equal to 0. Now, we can say the same thing is probably going to be true in the x direction. Teeter-totters don't start to suddenly accelerate to the left or to the right and shoot off across the playground. They stay in one place. So they're at rest, and they stay at rest in the x direction. So that means we can say the net force in the x direction is also equal to 0. But if you look at this teeter-totter we've drawn, you know, although it might not accelerate in the x direction, and although it might not accelerate in the y direction, it's going to start moving, right? Because the student over here is so much heavier than the student over here, this teeter-totter is probably going to start to rotate. So although the net force on this thing is 0, the system does have a net torque. So it is not in full equilibrium. It's in translational equilibrium because the sum of the forces is 0, but it's not in complete equilibrium, meaning it won't start to rotate, but it won't stay completely at rest. It may start to rotate. In order for a system to be in equilibrium, it must have both translational and rotational equilibrium. So whereas we said the condition for translational equilibrium was that the sum of the forces was 0, we say that the condition for rotational equilibrium is the sum of the torques is equal to 0. Now, we haven't really talked about what a torque is yet, so I'm going to write that in here too. So a torque, which is a vector, is a force times a distance, and they need to be perpendicular to each other. So this T is for torque. To get a torque, I need a force and to result in a torque, that force needs to be a certain different distance from some pivot point. And one little adjustment I'll just make here. Although torque is a vector, this formula doesn't really tell us the direction of the vector. This formula is only really useful for finding the magnitude of the torque. I'll tell you in a moment how to find the direction of torque. So the adjustment I'm going to make is I'm going to take off that vector hat. Torque is a vector, but this equation doesn't tell us the full vector. The next thing we might ask about torque is its units. Well, we can figure that out fairly easily. Force is measured in newtons. Distance is measured in meters. So torque will be force times distance, or newtons times meters, also known as Newton meters. So units of my torque are Newton meters. Now, to help you get a bit of an intuitive understanding of torque, I want you to consider a time when you were trying to unscrew something, a bolt or a nut maybe, and you might have found that it could have been hard. And one thing you can do to make it easier is you can get a longer wrench. Maybe not all of you have had this experience, but those of you who have used wrenches before will know that if you're using a really, really tiny wrench, it's hard to get something tight or to unscrew something that's tight. And a longer wrench will help with that. That really comes down to torque. To tighten a bolt or a nut to make it secure requires a certain amount of torque. You can think of torque as like tightening power. Or to loosen something that's already been tightened will require a certain amount of torque. Which means you need to apply a force. That's you pushing with your hand on the wrench. And you'll get more torque if that force is a further distance from the nut or the bolt that you're trying to tighten. So a really long wrench puts that force really far away from the nut, which gives you a much greater torque than a small wrench would, which has your force much closer to the nut or the bolt. So let's look at a specific example like this. A torque of 24 Newton meters is needed to tighten a nut. If a person can apply a force of 100 newtons, what length of wrench is required? So if I can push this hard on my wrench, how long does my wrench have to be so that I can generate this much torque to adequately tighten this nut? Okay, well, we know torque is force times distance, and they have to be perpendicular. So if I want to create a torque of 24 Newton meters, that means that's going to go here, 24.0. And if I can use apply a force of 100 newtons, that's going to go here. And then there's my R, the length of the wrench. And if I rearrange this and I solve for R, I get 0.24 meters. So if I have a wrench that's 24 centimeters long and I push with 100 newtons on the end of it, I'll generate the right amount of torque for this particular nut to get it tightened to where I need to get it tightened to. Now, this little symbol here, we haven't really talked about much yet, but I'll mention it in the context of this example. What that symbol means is that to create a torque, your force and your distance need to be perpendicular to each other. So imagine we had a wrench like this. Okay, so here's my wrench, and I've got a nut in here that I'm trying to loosen or trying to tighten. Well, so in order to loosen or tighten this, I need a torque, which means I need to apply a force to the wrench. And to do that, most of us would probably apply a force over here. Notice how that force, which is going in this direction, is perpendicular to the length of the wrench, which is in that direction. There's a 90-degree angle there. That's what this formula needs, that perpendicular symbol there. And that's how most of you would use a wrench. If you'd never used a wrench before, you had no idea what you were doing, and you tried something silly, like pushing on the wrench this way, that would not create any torque because this force is parallel to the distance along the wrench. They're not perpendicular, so it won't make any torque. In order to create torque, a force needs to be a certain distance away from the rotation point, and it needs to be perpendicular to that distance. Okay, the next thing about torque is a vector quantity. So it has direction. Right, in this example above, I'm trying to tighten a nut, which means not only do I need 24 Newton meters of torque, but it needs to be in the right direction. I'm probably going to want to be trying to twist the nut this way in order to tighten it. If I twisted the other way, even if I used 24 Newton meters, I would be unsuccessful in tightening the nut. So the direction of a torque can be clockwise or counterclockwise. And the convention we say is that clockwise is a negative direction. So torques that are trying to twist things clockwise, we call those negative torques. And a torque that's trying to twist something counterclockwise, we say that's a positive torque. Okay, now before we go on and do a few more examples, I want to kind of introduce you to a little bit of vocab, a little bit of a couple phrases that are going to come up. Maybe not right away in this lesson, but later on as we investigate torque a little more. I want to sort of plant the seed in your brain for some of these ideas so that when they do come up, they're not totally fresh. One thing I want to talk about is center of gravity. So in an object, say this wrench, for example, gravity acts everywhere. Gravity is pulling on every single atom in this wrench. There's an atom here that has gravity pulling on it, and here, and here, and here, and here, and here, and here. Every single atom you can imagine in this wrench has gravity pulling down on it. But rather than drawing a million little FG arrows going down, we tend to just draw one sort of at the middle of the object. The average place where gravity will act. Yep, on a normal object, there's going to be some gravity force to the left of the middle and to the right of the middle and above the middle and below the middle. But on average, Fg kind of acts at the middle of a normally shaped object. So we can think of the center of gravity as the average location of an object's mass. The average location of an object's mass, and it's where we draw Fg on that object in a free body diagram. Now, we're going to do a lot of problems coming up that have beams in them. So sort of a long, slender piece of material like wood or metal that's designed to support something. A great example would be in the teeter-totter we looked at up here. The main part of a teeter-totter is this plank or this beam. And this beam, like most beams or planks on teeter-totters, is what we would call uniform. Uniform means it's the same everywhere. The analogy I like to give is with school uniforms. If you're in a school where they have school uniforms, students will look the same everywhere. Doesn't matter what classroom you go into, doesn't matter what corner of the classroom you look at, students will look the same. They are uniform. Similarly with this beam here, right? Most teeter-totters are constructed so that no matter where I look on this beam, it looks the same. It's always made out of wood. It's always the same shape. It's always the same thickness. I'm not going to run into a situation where I find a teeter-totter where the beam is like square on this end and round on this end, or wood on this end and metal on this end, or really thick on this end but really thin on this end. That's rare. The planks on teeter-totters tend to be uniform. They tend to be the same everywhere. And that's an important concept on the topic of torque. So a uniform beam is the same everywhere. What's the same? The material, the shape, the density, the thickness, etc. Now the last little seed I want to plant is that of an arbitrary position of rotation. And this won't really become relevant until a couple lessons from now. Because most of the things we've looked at today, it's obvious where they rotate. This teeter-totter, the place where it rotates, the place where there's a pivot happening, where there's literally a hinge on the teeter-totter, is right there in the middle. We'd call that the pivot or the point of rotation. This wrench, the place where the wrench rotates, the place where the pivoting is happening is at the nut or the bolt right there. That's my rotation point. And it's pretty obvious that's where the rotation is happening. But we will come to situations where it's not obvious where rotation is going to happen. We can sort of zoom forward here. Here's an example of a truck going over a bridge. This bridge is not designed with any hinges or anything like that. It's not obvious where this bridge should rotate. But if we're calculating torque, we need to have a pivot in mind. Because to calculate torque, we need to know the force and the distance from the pivot. So it turns out that the location of the pivot is totally arbitrary. You can choose it to be wherever you want. So when you're looking at a situation like this truck down here, and you don't see an obvious hinge, you can pick your pivot point to be here, or here, or here, or here, or anywhere you want. You just need to pick a pivot point and stick with it for that problem. And the location is arbitrary, meaning it doesn't matter where you pick it. Even for this teeter-totter up here that has a pretty obvious pivot point, if I wanted to look at all the torques on this teeter-totter and find the net torque on the teeter-totter, I could, if I wanted to, choose this as my pivot point. And I could measure all the distances from there. Or I could pick this, or I could pick this. And I would get the same net torque no matter how I do it. So this idea of an arbitrary position of rotation just means you can pick the pivot point to be wherever you want it to be when you're calculating torque. No, the pivot point, remember, is the place you measure R from. Okay, so with those seeds planted, with those ideas in mind, let's go and do a couple of examples. So here we have a sine with a weight of 350 newtons, hanging from a pole which has negligible mass. The pole is attached to a wall through a hinge and then supported by a vertical rope. All right, lots going on here. We want to find the tension in that rope and the supporting force provided by the hinge. Now, I'm going to break one of my rules here just because I have sort of limited space to do my work in this problem. We're going to start with a free body diagram. Rule number 1 of a free body diagram is the body must be free, meaning pick an object to draw a free body diagram for and then draw only that object. So in keeping with what we've been doing, we're going to pick an object that has that is in equilibrium and that has all the forces acting on it. So I think the object we're going to pick here is this pole. I expect that pole to be in equilibrium. Based on what I know about signs and hanging them, I don't think that pole is going to accelerate up or down or left or right. And it doesn't look to me like that pole is going to start to rotate one way or another. So it should be in translational and rotational equilibrium. The pole also seems to have all the forces acting on it, right? This sign hanging from this piece of rope, that's going to be pulling on the pole. This piece of rope, that'll pull on the pole. This hinge, that's attached to the pole. So all the things in this problem seem to come together at the pole. So the pole is the object I'm going to do my free body diagram for. Now, because I don't have tons of space, I'm tempted to just draw my free body diagram on top of the existing. But actually, you know what? Let's set a good example here. Let's do this properly. It might be a little tight for space, but let's see if we can do it. I'm going to draw that pole again. And I'm going to draw the forces acting on it. So there's the force of the sign, which is 350 newtons. That's acting in the middle of the pole, and it's going down. Okay. There's the tension in the rope at the end. That's acting at the end of the pole. And that's going up. Ft for tension. And then over here, I have this hinge. And that hinge is capable of exerting some forces too. Now let's think about what way that hinge might be pushing on this pole. If we consider the free body diagram as it currently stands, imagine taking, just a stick like that. And then creating a scenario where something's pulling down on the stick in the middle and something's pulling up on the stick over here. What is that stick, as this diagram is currently drawn, what is that stick going to now try to do? Well, I think the stick is going to try to rotate this direction. So what this hinge over here is doing is it's stopping that from happening. It's stopping this end of the stick from falling down. So how would the hinge stop that end from falling down? It would do that by pushing up. So there's my hinge force. Okay, so those are all the forces acting on this pole. I've got the hinge pulling it up, I've got tension pulling it up, and I've got the weight of the sign pulling down on it. Now, I'm going to apply my equilibrium condition. Right? I know that this pole is not going to rotate. From looking at the diagram, I can tell that. It's going to stay at rest. So because it's not going to start rotating, I know the sum of the torques is equal to 0. There's no net torque on this pole. So if that's true, let's write out all the torques. Well, first of all, if I'm going to start calculating torques, remember, torque is force times distance, and they need to be perpendicular. And this distance is the distance from my rotation point. So in this scenario, where's the rotation point? Where are things going to be rotating about? Well, that's the hinge. So I'm going to just add that to my free body diagram. I usually do that with a circle and an X through it. Shows me that that's my rotation point. So let's look at my 3 forces and the torques that they might create. This force, the hinge force, is pulling up. But then I have to ask myself, what's the distance between that force and the rotation point? Well, it happens to be 0. That hinge force is acting right at the rotation point. There's no distance between where the hinge acts and where the rotation happens. So although the hinge creates a force, it's at a distance of 0 from the rotation point, so the torque will be 0. So it does not appear over here when I add my torques together. Let's look at the next force. This 350 newtons. That's a force. Now, what distance is it from the rotation point? Well, that's this guy over here, 1.3. So let's write that torque down in my sum of torques. I have a force of 350 times a distance of 1.3 from my rotation point. And because torque is a vector, I've got to pay attention to whether these things are positive or negative. So this 350 is trying to, my rotation point is over here. The 350 is trying to rotate this pole in this direction, like that. That is clockwise. So this is a clockwise torque. We said clockwise is negative. So this first torque I've written down is going to be negative. Okay, I've got one more force that might create a torque, and that's this guy over here. So the force is Ft. And remember, I have to take that force and multiply it by the distance from the pivot. It happens to be a distance of 2 meters from the pivot. So I'm going to have Ft times 2. And that is trying to rotate my pole in a counterclockwise direction. So that is going to be a positive torque. And because it's in equilibrium, the sum of those torques is equal to 0. So now I can go ahead and solve for Ft. I get Ft equals 350 times 1.3 divided by 2, or Ft equals 227.5. Or if I round to 3 sig figs, I get 228 newtons. All right, that's pretty good. Now, so what do we do here? We said that because this whole scenario is in equilibrium, meaning it is at rest and it's not going to start rotating, that means the sum of the torques has to be 0. So I went and I found all the torques. After drawing a free body diagram, I said, well, this force acts at a certain distance. I did that there. And then I said, well, this force acts at a certain distance from the pivot. I put that here. And that slowly, by following that process, I added up all the torques and I set them equal to 0. Remember that my hinge force, although it's there as a force, it did not create a torque because its distance from the pivot point was 0. It acted right at the hinge. Then by just solving that and doing some simple algebra, I was able to find out what the tension force was. Now the next thing I'm being asked is for the force provided by the hinge. So I want to try and find out what this guy is. However, I kind of just used an equation, and H never appeared in that equation because it didn't create any torques. H goes through the pivot point. So it doesn't create a torque, so it won't ever appear in this equation. So how can I get an equation that does have h appear in it so I can solve for it? Well, if this object's in true equilibrium, that means it's not just in rotational equilibrium, but also in translational equilibrium, then I also need to have that the sum of the forces is equal to 0. And in this situation, since all the forces are in the y direction, I'll just say the sum of the forces in the y direction has to be equal to 0. So that means I have h, which is in the positive y direction. I have 350, which is in the negative y direction. And I have tension, which is in the positive y direction. And those have to add up to 0. Then solving that gives me that h equals 122.5. Or if I round to 3 sig figs, 123 newtons. And you know what? Force is a vector, so I should probably include my direction here. We figured out at the very beginning that h was going up, so I should probably include that in my answer too. So 123 newtons up is the supporting force provided by the hinge. All right, so the idea here was when I have a system or an object that is in equilibrium, meaning it's not going to start rotating and it's not going to start translating, then I can say both the sum of the torques is 0 because it won't rotate, and the sum of the forces is 0 because it's not going to start translating. And by plugging things in, I can solve for a variety of different things. I basically have two formulas or two equations I can work with, so I'm able to find two different things, the tension force and the hinge force. And then remember, we started this problem by picking one object to do a free body diagram for. We picked the pole because it was in equilibrium and because it had every other force acting on it. So it allowed us to pull all the different information from the question together into one place. Let's look at another example. Two students sit on opposite sides of an 800 Newton teeter-totter. Student 1 has a mass of 65 kilograms and sits at the very end of the teeter-totter. So let's add this to our diagram over here. Student 2 has a mass of 90 kilograms. How far from the pivot should he sit in order to achieve equilibrium? So I think we know if my heavier student with 90 kilograms goes all the way at the end, the teeter-totter on their side is going to sink down. But if we want to keep this teeter-totter perfectly balanced in rotational equilibrium, the student might have to sit somewhere closer to the middle, over there. We don't know exactly where yet, so let's draw them in somewhere, and then we'll figure out the exact location. So we're trying to find how far this guy is from the pivot, from the center of the teeter-totter. So I'm going to call that distance x. All right, so free body diagram. The plank of my teeter-totter is in equilibrium, and it has all these forces acting on it, both students and the supporting force of the fulcrum. So I'm going to draw a free body diagram for the plank of my teeter-totter. It's got an FG over here, which is going to be 65 times 9.8, or 637 newtons. and it's got an FG over here, which is going to be 90 times 9.8, or 882 newtons. Then there's a supporting force from the fulcrum in the middle of the teeter-totter, pushing it up. I don't know exactly what that's going to be. I guess I could figure it out. Since this teeter-totter has no net force in the y direction, it's not going to be accelerating up into the air or burrowing down to the ground. This guy has to cancel out these two, so it should just be 637 plus 882. However, I don't think I even actually need that information to solve this problem. So I can just call this Fn for now. And if I'm going to start calculating torques, I need to have a rotation point, a pivot in mind. And in this teeter-totter, I think the obvious thing to choose is right above the fulcrum where the hinge on the teeter-totter would be. So a little circle with an X through it. There's my rotation point. Okay, now let's go to my torque formula. This teeter-totter is going to be in rotational equilibrium. That's the whole goal, is to have it balanced. I'm trying to figure out where that second student needs to sit in order to have that happen. So wherever he ends up sitting, we need to have the sum of the torques is equal to 0. So let's look at these forces and see that the torques they create. I've got a force of 637 newtons at a distance of half the length of the teeter-totter, so 1.3 meters from the pivot. So 637, that's my force, distance of 1.3 meters. And is that guy going to create a positive or a negative torque? Well, this guy is trying to spin the teeter-totter this way, so that's counterclockwise, so that'll be a positive torque. Now let's look at my 882. That's my force. It's at a distance of x from the pivot. So and it's going to try and spin the teeter-totter clockwise, so it'll be a negative torque. So a negative torque, that's 882 times x. Now, I should just be able to solve this for x. Remember, when I'm using this torque formula, I do have to have, in order to create a torque, my force and my distance need to be perpendicular to each other. So we should just double check that. And indeed, down here in this example, yes, this force is up and down. The distance I used to the pivot was left-right. This force was up and down. The distance I used to the pivot, x, was left-right. So my forces and my distances were all perpendicular. It's just good to double check that. Solving this equation, I get that x should be equal to, what would it be? Negative 637 times 1.3 divided by negative 882. That's what I get if I just leave x where it is and move everything to the other side of the equation. So that gives me x equals, if I round it to 3 sig figs, 0.939. So 0.939 meters is x. It's how far this student needs to be from the pivot point in order for that teeter-totter to be in equilibrium, to be not starting to rotate one way or another. Okay, last question. This one gets a little tricky. This one pulls in the idea we were talking about before of an arbitrary position of rotation. This is the first question we've done where there's not an obvious rotation point, right? Up here we had a teeter-totter, which was obviously rotating at that central point. Here we had a wrench which was rotating around the nut or the bolt it was tightening. Here we had a case where there was a hinge. That's going to be where the rotation happens. Here we had another teeter-totter. Rotation is going to be in the middle. In this question, we no longer have an obvious rotation point with this truck on the bridge. That's okay because rotation points are arbitrary and we can pick the pivot point to be wherever we want. That's nice. It just kind of feels weird the first time you do it. So let's look at this question. A 3,500 kilogram truck is parked on a bridge as shown. If the bridge deck itself has a mass of 6,500 kilograms, find the supporting force provided by each of the two support posts. Okay. Free body diagram. Here's my bridge deck, right? The bridge deck is going to be in equilibrium unless this bridge is falling over. And the bridge deck has all the forces acting on it. So that's the object I'm going to use for my free body diagram. And so the bridge deck itself has some weight. Its weight is going to be 6,500 times 9.8. So 63,700. Then we've got the weight of the truck. Truck's not quite as heavy as the deck itself. It's over here. It is going to be a weight of 3,500 times 9.8. So 34,300 newtons. And then I've got the two support posts, and those are both going to be pushing up, stopping the bridge from falling down. So I'm going to call this one L for the left support post, and I'm going to call this one R for the right support post. I don't actually know if they're going to be the same length. In fact, I kind of suspect, because the truck is closer to the right-hand side, I think the right-hand support post is going to have to be trying a bit harder. It's going to have more force on it. So this guy is probably going to be a little longer than this guy. That's what I'm guessing at this point. I don't need to incorporate that in my diagram, though. All right. So now, because this bridge is in equilibrium, it's not going to start rotating one way or the other, assuming it was designed well. The sum of the torques should be equal to 0. But when I calculate those torques, I need to take forces and multiply them by distances. And those distances are measured from a rotation point. So I need to pick a rotation point. Now, there's a little bit of skill involved in doing this. We could just pick our rotation point to be in the middle. That's kind of like been a pretty common thing we've done so far, looking at all these teeter-totters. If I pick my rotation point in the middle, then this guy will be a certain distance from it. And this guy will be a certain distance from it. Which means I'll have one torque that has an L in it, and I'll have one torque that has an R in it. So my formula here is going to have an L and an R. Two things I don't know, making that equation impossible to solve. So what I'm going to do to make it so that my equation only has one of those two forces appear in it, I'm going to pick my rotation point to be at one of those forces. So I'm going to actually pick my rotation point to be here. That means if that's my rotation point, L is at a distance of 0 from my rotation point. L acts exactly at the rotation point. So L will not create a torque at all about that rotation point. So L will not appear in this formula because it doesn't create a torque. That means R should be the only thing in this formula I don't know, and I should be able to solve for it. Let's try that. Okay, so L creates no torque, but this weight of the bridge certainly does. And it's at a distance of whatever that is. Well, the whole bridge is 15, so that halfway point where FG is going to act, because it's a uniform bridge, I think, is going to be 7.5. So my first torque is 63,700 times 7.5. And that guy is trying to rotate my bridge. This force here is trying to rotate my bridge in a clockwise direction. So that's going to be a negative torque. Then I've got this guy here, also trying to rotate my bridge in a clockwise direction. So also a negative torque. So I'm going to have a negative torque that's caused by a force of 34,300 at a distance from the pivot of, okay, well, the whole bridge is 15. The truck is 5 from the end. So from the pivot point to the truck should be 10. So here to here is 10. That makes sense. And then the last force that's creating a torque about this pivot point is R. R is trying to rotate the bridge in a counterclockwise direction. So R is going to create a positive torque. And that torque is going to be the force, R, times the distance from the pivot, 15 meters. So that is the sum of all my torques. And because we're in rotational equilibrium, the sum will equal 0. There will be no net torque. So I should be able to then go through and solve for this. If I kind of take this term here and I leave it where it is and I move everything else to the other side, I should get R equals 63,700 times 7.5 plus 34,300 times 10. Divide that all by 15. And I get R equals 54,717. Or if I round to 3 sig figs, we'll just call that 54,700 newtons, and that support is pushing up. Okay, so that is the supporting force provided at the right-hand side of the bridge. That's R. But I still need to solve for L. I was asked to find the force provided by each of the 2 support posts. So how am I going to find this L? Well, we got a couple options. When I picked my rotation point to be at L, I was able to use this formula to find R. So if I picked my rotation point to be at R, I could probably use that same formula to find L. And indeed, that would work. I could just redo the exact same process I did, but move my rotation point from here to here. That would help me find L. And that would work totally fine. However, I want to kind of remind you guys that when something's in equilibrium, it's not just in rotational equilibrium, it's in translational equilibrium as well. So the sum of the torques being equal to 0 is not the only information we have available to us. We also know the sum of the forces is 0. So another way we can solve this problem is to look at the forces. In this problem, all the forces are in the y direction. So in the y direction, I have L, and it is in a positive force. So I have positive L. I have 63,700, and it's negative negative 63,700. And I have 34,300 and it is positive. And I have R and it's positive. So that is the sum of all the forces in the y direction, and they have to equal 0. Remember, when I was doing torques, every force had to be multiplied by a distance, and the direction was based on clockwise or counterclockwise. When I'm doing forces, I simply take the force as it is. I don't multiply it by any distance, and the direction is just positive or negative based on whether it's up and down. So that's another reason why I kind of like to use this second formula, the sum of the forces, when I can, is it's just a simpler formula to use. I'm less likely to make mistakes doing it. So if I take this, and I already know that R is, so this R here is this number up there. If I plug that in for R and then solve for L, I should get that L equals, and I've just realized that I've made a mistake here. That mistake was that both of these two forces are going down. So they should both be negative. I wrote one as negative and one as positive. So let's go in and fix that. This positive should actually be a negative. That cleans things up a bit. And now I'm able to calculate that L is equal to 43,300 newtons if I round it to 3 sig figs. $43,283. So 43,300 newtons, and L was also in the upward direction. Okay. So just a reminder, the things that were new in this last example was when we had a situation, we're looking at our original diagram, there was no obvious rotation point. There was no hinge shown. So we had the pleasure of being able to pick the rotation point ourselves. We happened to pick it here. There's other places we could have picked it, and they would have gotten us to the exact same answer in the end. Also, remember that you have, when something is in true equilibrium, meaning rotational equilibrium and translational equilibrium, you have two conditions at your disposal, two formulas. One is that the sum of the torques is equal to 0, meaning it's not going to suddenly begin to rotate. And the other is that the sum of the forces is equal to 0, meaning that it's not suddenly going to start accelerating up or down or left or right. So that concludes our lesson on torque, bit of a long one. The next thing we're going to start thinking about, to give you a little bit of a spoiler for the next lesson, is what happens when I have a force that's acting at a distance from a pivot point, but they're not quite perpendicular, right? We said that when the force is parallel, I get absolutely no torque. When the force is perpendicular, I get a torque. What happens if it's sort of partly between parallel and perpendicular? What if that force is kind of at a bit of an angle? That's what we're going to tackle in the next lesson.